This video is going to cover section 3.5 on rational functions. The definition of a rational function is a function that is a quotient of polynomial functions. So we have spent the last several sections talking about polynomials. So now we're going to look at what happens when we take two polynomials and create a fraction. So p of x would be a polynomial, q of x would also be a polynomial, and we're going to divide them. So because we are creating a fraction, we could possibly have restrictions in the domain because we talked about earlier, the denominator of a fraction is never allowed to be 0. So this is our definition of a rational function. It'll be a fraction of polynomials, and the domain would be the set of all x values such that the denominator is not equal to 0. So we're going to start by locating points at which the denominator is 0 to find the domain, and this time when we identify the domain, they are going to ask you to put it in what we call set builder notation, which looks like this instead of interval notation. Alright, so here are a couple examples of just finding the domain. So f of x equals x squared plus 2x divided by x squared plus x minus 2. So this would be an example of a rational function. So if we're just finding domain, we want to make sure that the denominator, x squared plus x minus 2, is not equal to 0. So this will factor into x plus 2 times x minus 1. So setting each of these factors equal to 0 means we have to restrict the value, so this would mean x cannot be negative 2 and x cannot be a 1. So when we write that in set builder notation, it's the set of all x such that x is not equal to negative 2 or 1. I believe in my math lab it'll be set up for you where you just have to type the restricted values in the box. This part will already be there. Okay, but just so you understand when you see that what it means. Let's do one more. F of x equals x plus 1 divided by x squared plus 4. So again, if it's a rational function, we need to find the domain by looking for the values of x that would make the denominator 0. So we know x squared plus 4 is not allowed to be 0. This time if I solve that equation, we could use the square root property. This won't factor, right, because it's a plus, a sum of squares. So we could subtract 4 to the other side and then square root both sides. But when I move the 4 over, I get a negative. So when I square root that, I get an imaginary number. So the only restricted values are imaginary, means there are no real value restrictions. So if we're talking about domain, we're talking about wanting to eventually look at a graph, so we only care about real solutions. So if there are only imaginary solutions and not any real solutions, that means there are no domain restrictions. All right, so let's start to talk about what graphing rational functions looks like. All right, so let's look at this first example here. This is just a very basic, the most basic rational function you could possibly see. F of x equals 1 over x. So my domain of this would be the set of all x such that x is not 0. That is the denominator. If I look at the graph of this function, since x cannot be 0, I'm going to draw a dotted line as the line x equals 0 right here, just to remind myself that if I'm going to plot some points that I can't use that x value, so it's not going to ever touch this line. I can use numbers on the left and numbers on the right, but I can't use 0. So we're going to draw a little dotted line through here. That line, the line x equals 0, is what we're going to call a vertical asymptote, meaning that the graph is going to move close to that number or that line, but it's never going to touch it. Okay, we'll talk about what this says here in just a second. Okay, let's just say I was trying to get an idea of what this graph looked like. So I can't pick 0 to plug in because I get an undefined value, but I could plug in some negative numbers and I could plug in some positive numbers. So let's just go through and see what that would give me. So I'll say I plugged in -1. So if I plugged in -1 in for x, I would get a -1 answer. So -1 would be right here. If I plugged in -2 as a value for x, 1 over -2 is -1/2. So if x were -2, we would be down here at -1/2. If x were -3, we'd be down here at -1/3. What if x were -1/2? Like right here, we would be down here at -2, right? 1 divided by 1/2, 1 divided by -1/2 is -2. So we kind of see our points line up in this shape, right? So I would kind of draw in my curve, noticing I see that the pattern shows me that I'm moving down, but I'm never going to actually touch this line because I can't use the value 0. And no matter how far I move this way, no matter what number I choose for x and plug it in, I still get a negative number every single time, right? X can be -100. I would get -1 over 100. So I'd always be below this y = 0 line, this x-axis. Similar things happen on the other side. If I plug in +1, I get 1. If I plug in +2, I get 1/2. +3 is 1/3, right? +1/2 is 2, right? So we see the points kind of line up in this sort of shape again. The closer I get to the x = 0, the higher I go. And no matter how big I choose my x, I always get a positive number. So my graph stays on the top of this x-axis. All right, so we see a few things happening here as I get close to these x-axis and y-axis in this example. So we mentioned that the vertical line x = 0 is called a vertical asymptote because it's a restricted value that I'm not allowed to cross. So as I look at this graph, we can kind of notice some patterns in the behavior of x and f of x. So as x approaches 0, which is this line, this little negative sign means from the left. So if I go back to my graph here and I go to the left of that line and I follow my graph, so as x is moving closer to 0 from the left, what do I see happening to f of x or to y? It's going down. So we could say that as x gets close to 0 from the left, the function values approach -infinity. We can also see that as x approaches 0 from the right, this little plus sign means from the right side. So here's if I start somewhere on the right of 0 and then move back towards 0, my function values are going up high. So in that case, the function values f of x approach +infinity. Right? Also, there's some behavior going on in regards to this line y = 0 right here. We said as I move far left and far right, I'm getting close to that line, but I'm not ever going to actually hit it. So that line y = 0 is what we call a horizontal asymptote. Horizontal asymptotes predict end behavior. Vertical asymptote identify domain restrictions. Okay, so there's a different purpose. So this time, because it's predicting end behavior, we're looking at what happens as x goes toward -infinity or +infinity. So as x goes toward or approaches -infinity, so if my x's get really, really small this way, my function values seem to be getting close to 0. They're never actually going to reach it, but they're going to get close to it. So as x approaches -infinity, f of x or y's approach 0. In the other direction, as x approaches +infinity, my function values or the y values approach 0. Same thing. They're just coming from up here, right? But they're still getting close to that y value of 0. All right, so this first example is going to give you a graph of a rational function and ask you to fill in the blanks in regards to that type of behavior. So we need to understand how to read that. So if this is my given function, they're telling us here that the vertical asymptote is here at this dotted line, -3. There's also a vertical asymptote over here at this line, x = 1. And the horizontal asymptote is the x-axis again at y = 0. So fill in the blanks. So they give us as x approaches -3 from the left, f of x approaches, and then there was a blank. So I would go over to my graph. Here's -3. The little negative sign behind it means start on the left of it. So go to the left and find the graph, and then follow the graph as you're getting closer to -3. And what's happening to y? You're going down. So the f of x approaches -infinity. as x approaches 1 from the right, okay, so here's my x equals 1, start on the right of it, find the graph, move toward 1, what's happening to f of x? It's going up, so we could fill in the blank as f of x approaches positive infinity. And then this last one, as x approaches negative infinity, so that means on the far left of your graph, as x is moving as far left as you can go, if I follow my graph to the far left, I see my y values underneath the x-axis, but they're getting close to it, so they're approaching 0. This notation, if you eventually take a calculus course, you will see again in regards to understanding limits. All right, so next our goal here is to try to learn how to graph a rational function, so we need to know how to look at the equation and locate where those asymptotes are. So this first procedure is how to identify or locate vertical asymptotes and holes. All right, so in the few problems in the homework, when they're just asking you to find vertical asymptotes and holes, you could have one or both. When you actually get to the graphing problems, they're going to assume that there are no holes. Okay, so there won't be any holes when you actually graph, but there could be, and this is going to show you how to know if there are and where they are located. All right, both vertical asymptotes and holes are located at x values in which f of x has a domain restriction. In other words, the values of x that cause the denominator to be 0. Okay, so if there's a restriction in the domain, it is either going to indicate a location of a vertical asymptote, as we saw in the last example, or possibly a hole in the graph. So how to know which is which? If the factor in the denominator cancels with the identical factor in the numerator, then there's going to be a hole in the graph at that x value. If the factor in the denominator does not cancel with anything in the numerator, then there's going to be a vertical asymptote at that x value. Okay, so here's a couple of examples. X squared plus 2x divided by x squared plus x minus 2. So in the numerator, this was that earlier example where we're just finding domain. We set the denominator to 0 and indicated our restrictions. All right, here we're going to identify if those restrictions are holes or asymptotes. All right, so here we would want to factor the top, which we can factor out x, that leaves x plus 2. We would factor the bottom, that factors into x plus 2 times x minus 1. So notice when I have both in factored form, the factor x plus 2 cancels out. So since the x plus 2 cancels, right, if that factor cancels, there's going to be a hole in the graph at the x value that would cause that to be a 0. So there would be a hole at the x value negative 2 because that factor cancels out. However, this x minus 1 does not cancel. So since the x minus 1 factor does not cancel, that means there's a vertical asymptote at the x value that makes this 0. So at x equals 1. All right, let's do one more example of that. F of x equals x over x squared minus 16. So the top just being x, there's no factoring to do. The bottom, however, I can factor into x minus 4 and x plus 4. Nothing cancels, right? You can't cancel anything out, meaning there are no holes. However, you do have factors in the denominator, so if you were to set those to 0, those would give you your vertical asymptotes. So if I set x minus 4 equal to 0, I get x equals 4, and x plus 4 set to 0 gives me x equals negative 4. So both of these would be vertical asymptotes in this example, and there would be no holes in the graph. All right, our next procedure is how to locate where the horizontal asymptotes are. So if we have a rational function, quotient of polynomials, to locate horizontal asymptotes, we compare the degree of the top, p of x, to the degree of the bottom, q of x. And there are 3 scenarios. Case 1, if degree of the top less than degree of the bottom, y equals 0 will be the horizontal asymptote. In other words, on the ends of the graph, the end behavior, the graph will be getting close to the line y equals 0. If the degree of the top equals the degree of the bottom, y equals, so this is the equation of a line, y equals leading coefficient of the top divided by leading coefficient of the bottom is a horizontal asymptote. So this will just be a number, y equals some number that will be a horizontal line that would predict what's happening on the ends of the graph. If the degree of the top is greater than the degree of the bottom, there is no horizontal asymptote. So when they're just asking you to identify the horizontal asymptotes, if that's the case, you're just going to say there is none. However, if you're graphing a problem where this happens, there is a different kind of asymptote, and we call it a slant asymptote, and you find it by division. So if this is the case and you're sketching the graph, there's going to be a slant asymptote found by division, and its equation is y equals the quotient of p divided by q. So you're going to actually divide q into p. You can do long division or synthetic, and you just ignore the remainder. The remainder doesn't matter, and it's just whatever you get as the quotient. We will do an example of this later on. All right, so these next three are just asking you to find the horizontal asymptote, and that is it. F of x equals 15x divided by 3x squared plus 1. So in this problem, since the degree of the numerator is 1 and the degree of the denominator is 2, that means the degree of the top is less than the degree of the bottom. So that's case 1, so the HA means horizontal asymptote would be at y equals 0. In part B, it's slightly changed to be 15x squared divided by 3x squared plus 1. So in this problem, the degree of the top is 2, the degree of the bottom is 2, which means the degree of the top equals the degree of the bottom. So that means the horizontal asymptote is found by finding the equation y equals the leading coefficient of the top is 15, the leading coefficient of the bottom is 3. So you take 15 divided by 3, which is y equals 5. So it's a horizontal line up at y equals 5 that is going to predict the end behavior of that graph. And in part C, the top is 15x cubed divided by 3x squared plus 1. So the degree of the top is 3, the degree of the bottom is 2. So if the degree of the top is greater than the degree of the bottom, we would just simply say there is no horizontal asymptote. If we actually had to graph this function, we would then want to divide the bottom into the top, and in this case you would have to use long division because this is not the form x minus c or x plus c. All right, so how do we put all this together and actually draw a graph? All right, so here are the steps we're going to follow. Step 1, find the y-intercept. That's an easy point to plot, so you can just plug in 0 for x and solve, and you'll have a point unless it's undefined at 0. Second, find the x-intercepts. That means in a rational function, set the numerator equal to 0 and solve. Step 3, find the vertical asymptotes. That's set your denominator equal to 0 and solve. Any results of that, vertical asymptotes, are sketched as dotted lines on the graph. Step 4, find the horizontal or the slant. That's where we compare degree of top and bottom. We're going to sketch those also as dotted lines on the graph. Step 5, plot a few additional points if necessary. In my math lab, they'll set up a table for you and they'll give you the x's that you're supposed to plug in, and you'll just fill in the boxes from the table. And then step 6 is to sketch the graph between and beyond each vertical asymptote. So basically your vertical asymptotes our vertical asymptotes separate our graph into sections, right? They represent domain restrictions. So you can graph points on the left and right of them, but not at those points. So there should be a piece of the graph on the left and the right of every vertical asymptote. All right, so this first example, we're going to walk through these steps. F of x equals 4x divided by x squared minus 9. Remember, when you get to the graphing, they are assuming that it's already in simplest form, so there should be no cancellations. In other words, no holes to worry about. All right, so the first step, the y-intercept, means plug 0 in for x. So 4 times 0 divided by 0 squared minus 9, that's 0 divided by negative 9, or 0. You can plot that if you want to. Just go ahead and plot the y-intercept when you find it. X-intercepts, set the numerator equal to 0. So 4x equals 0, divide both sides by 4, we get x equals 0. So again, that's the same point right here. Vertical asymptotes, set the denominator, x squared minus 9 equal to 0. And then to solve, here we would factor into x minus 3 and x plus 3. So we would get x equals 3 and x equals negative 3. So these are the dotted lines right here, x equals negative 3 and x equals positive 3. Step 4, to compare degree of top to the degree of the bottom. The numerator has a degree of 1. The denominator has a degree of 2. So the degree of the top is less than the degree of the bottom, meaning the horizontal asymptote would be y equals 0. So I know you can't see it as a dotted line because it's on the x-axis, but this x-axis is a horizontal asymptote. And then step 5 is to plot a few additional points if necessary. So they would have set up a table and listed some x values up here. You would just use your calculator to plug them into the function and indicate the results. I do believe that if the results are fractions in my math lab, they are going to require that you enter a fraction. So make sure you keep it in fraction form. You may need to convert to a decimal on the calculator to know exactly where to plot them, but that you can't type decimals in this table, okay, and expect to get credit for that. All right. So I already had this point plotted, okay, so at negative 5, we were at negative 5, 4, so that's negative 1 and a 4, so that would be a point down here. At negative 4, negative 16 sevenths is negative 2 point something, so that's a little bit lower. So you can kind of see on the left side of this vertical asymptote, I'm going to have to kind of, my graph's going to be this little curve that doesn't cross it. As you get close to a vertical asymptote, you have to go down or up, so we're headed downward. And then this, the other way is predicting our end behavior at our horizontal asymptote, so it kind of slides close to this line. All right, negative 1 plugged in gives me a half, and positive 1 plugged in will give me negative a half. So at negative 1, we're at positive a half, and at positive 1, we're down here at negative a half. We already had this point plotted, so you can kind of see here that we're headed upward as I move toward the vertical asymptote, negative 3 from the right side of it, and we're headed downward because of this point being plotted here if I move toward positive 3 from the left. And then 4 and 5 are just a couple points on the other side of the x equals 3. So 16 sevenths, when I plug that in, that is a little bit bigger than 2 right here. And then 5/4 is 1.25, so it's about right here. So we can kind of see this section of the graph filling in up in this quadrant over here. The graphs on these for my math lab are multiple choice. So you will have to fill in your table, but once you kind of get a general idea of where those points are located, it's just choosing the right graph that is given. So you're not actually plotting yourself on the computer. All right, let's look at another example. F of x equals x squared divided by x squared plus x minus 6. All right. Step 1, find the y-intercept, plug 0 in for x. So that makes the top 0 and makes the bottom negative 6, so we get 0 again. X-intercept, set the numerator equal to 0. So x squared equal to 0, again gives me x equals 0. We should note here that this had a multiplicity of 2, so an even multiplicity means it's going to touch and turn around or bounce off the x-axis. So y equals 0, x equals 0, right? It's just this 1 point. Vertical asymptote, set the denominator equal to 0. So this would factor into x plus 3 and x minus 2. So my vertical asymptotes are going to be at x equals negative 3 and x equals positive 2. So x equals negative 3 and x equals positive 2. Vertical lines. Horizontal, we compare degree. The degree of the top is a 2. The degree of the bottom is also a 2. So this is the case where the degree of the top equals the degree of the bottom. So the horizontal asymptote is y equals, leading coefficient on top is 1, leading coefficient on bottom is 1. So y equals 1. So that's this line right here, y equals 1. Dotted line. All right, we're going to fill in our table for a few additional points. Negative 5 and negative 4 on the left of the negative 3. So when I plug in negative 5, we get 25 fourths, and when 25 14ths, and then when we plug in negative 4, we get 8 thirds. So we plot those values. We're up here above this line, so we kind of see that graph should sit above the y equals 1. Negative 2 and negative 1 are in between the two asymptotes. At negative 2, we land down here at negative 1, and at positive 1, we're down here at negative a fourth. So from here, remember, we're supposed to bounce off, so it would make sense that it heads down on this side, which means it would bounce off and also head down on this side. All right, so we get this sort of U-shaped graph in the middle. And then on the other side of 2, 3, and 4, we get 1.5 and slightly bigger than 1, so 1.5 here, and then just barely bigger than 1. So again, we're above that y equals 1 line, so this piece would slide in between these two dotted lines up here. All right, one more example. This one illustrates what happens when we have the slanted asymptote case. So x squared plus x minus 6 divided by x minus 3. So step 1, finding the y-intercept. When I let all the x's be 0, we're left with negative 6 divided by negative 3, which would be 2. So my y-intercept is 2, so I could plot that right here. X-intercepts, set the numerator equal to 0. We can solve this by factoring. X plus 3 times x minus 2 gives me x equals negative 3 and positive 2. So x equals negative 3 and positive 2 are my x-intercepts. So they can be plotted on my graph. Step 3, find the vertical asymptote. Set the denominator equal to 0. That just gives me x equals 3. So this has one vertical asymptote right here at x equals 3, the dotted line. Find the horizontal asymptote. Degree of the top in this case is a 2. The degree of the bottom is a 1. So in this case, we have the degree of the top greater than the degree of the bottom. So that's the case where there's not a horizontal, but that means there's going to be a slant. So we said if there's a slanted asymptote and we have to find its equation, we divide. We take the x minus 3 and divide it into the x squared plus x minus 6. This is of the form where we could divide by synthetic division, right? So the 0 of the denominator is 3, so that would sit out here. The coefficients 1, 1, negative 6, and we just do the synthetic division process. So this drops down the 1. 3 times 1 is 3, it would go here. Add is a 4. 3 times 4 is 12, would go here. And add is a 6. Remember, the last number is the remainder, and we're supposed to ignore it. We don't care about the remainder on a slanted asymptote. So these numbers would represent, this would be 1x plus 4. So our line, y equals x plus 4, that's the equation of the slanted asymptote. So we sketch that in just like we would draw in a horizontal line. We just have to, this is just a slanted line. This is a line with a y-intercept at 4 and a slope of 1. So the y-intercept up here at 4 and a slope of 1, we would go up 1 over 1. And we just connect the dots, right? And draw in our slanted line right here. All right, and then notice here's my vertical asymptote right here. I already had these 3 points. Both my x-intercepts and my y-intercept were already identified on the left of that line. So I kind of already know that if I have to connect these together, right, and I have to, if you kind of start out on this slanted asymptote, right, that you have to be close to that, and since the points you have to hit are below it, you would start close below it, come through, hit these points, and then after you hit this point, you're headed down, so you have to continue to head down here. So this piece is kind of already set because we had found our intercepts. So my table here only reflects points on the other side, 4, 5, and 6. So if I plug in a 4, I get 14. If I plug in a 5, I get 12. And if I plug in a 6, I get 12 again. So at 4, way up here at 14. At 5, we're down here at 12. And then at 6, we're also at 12. So these points are going to come through these 3 points up here and kind of slide between my asymptotes up in this section. All right, this is one of the longer sections of this course and one of the more difficult ones because there's a lot of steps and a lot to learn. So that is the end of section 3.5.